So today we're going to talk about changing variables in multiple integrals. So recall from Calc 1, we did U substitutions, remember, and those followed, well, my demonstration here below, right? We let x be some function of u, dx then, let's say g of u, then dx is g prime of u du, and we also change our limits, evaluating them. So C is G of A, D is G of B. And our goal is to do something similar for double and triple integrals. So I'm going to break this up into two videos. The first video will be mainly explanation, and I might leave the examples for the second video, just because this is a little more complicated and I want you to be able to focus on what we're doing here. We'll see how it goes. A planar transformation, T, is just a function that's going to transform one region, let's say G in one plane, into a region R in another plane by a change of variables. Figure 5.71 in the textbook, which is reproduced in the notes here, gives us a nice sketch illustrating this. So a transformation T is said to be 1-to-1, right? If for every point in our region R, there's only one point in region G that it could have come from, right? So in other words, for every x sub 1, y sub 1 in R, there is only one point u sub 1, v sub 1 in G, such that the transformation applied to u sub 1, v sub 1 gives us the point x sub 1, y sub 1. Now, why do we care about whether or not a transformation is 1-to-1? Well, we care because that determines whether or not it is invertible. So if our transformation T going from G to R is 1-to-1 in that domain G, then the inverse transformation, which we denote, as usual, capital T to the minus 1, then that's going to exist with domain R such that the composition of T with T inverse and T inverse with T give us the identity function. So in other words, what that means is that if I take some point, I don't know, let's just keep it simple and think about maybe one-dimensional, but we can do it either way. So let's say if x1, x sub 1, y sub 1, if that point is in R, then the composition of T with T inverse of that point gives us, that point back. And if we have a point u sub 1, v sub 1 that's in G, then the composition of T inverse with T evaluated at that point gives us that exact point back. That's what it means to have to be an identity function. Let's look at a quick example. So I'd like to determine the new region we get by applying the given transformation to the region G in the xy plane. That's the region bounded outside by the ellipse x squared plus y squared over 36 equals 1. So in other words, we have the ellipse and it's interior, everything inside it. The transformation we're going to use is x is equal to u over 2, y is equal to 3 times v. So how do we do this? Well, really all we do is we plug in the provided transform variables into the equation for the ellipse. So we're going to substitute in u over 2 for x and 3 times v for y. So we're going to get u over 2 quantity squared plus the quantity 3v squared divided by 36 equals 1. Okay, so that's going to give me u squared over 4 plus 9v squared over 36 equals 1, or In other words, I'm going to get u squared over 4 plus v squared over 4 equals 1. Using our handy dandy algebra skills, we can just multiply both sides of that little old equation by 4, and we obtain u squared plus v squared equals 4. And this is a disk of radius 2 centered at the origin. So what we've done here is we've transformed our ellipse into a circle. And in general, right, when we're trying to do something like this, to find our new region, we simply determine what happens on the boundary, and that's exactly what we did in this example. And everything else follows. So the idea here is that we want to transform the region we're integrating into one that's simpler for us. For example, here we transformed an ellipse into a circle. A circle, if we're, let's say, transforming to polar coordinates, is easier, right? All we have to do, r squared equals 4, r is going to range from 0 to 2, theta is between 0 and 2 pi, and we're integrating something simpler. Okay, we need some more tools before we can do this, and one of that major tool we're going to use is the Jacobian. So let's say we have our transformation t of uv, and it's x is going to, try that again. So that transformation t of uv is going to be the point determined by g of uv for the x coordinate and h of uv for the y coordinate. And g and h are assumed to have continuous first partial derivatives. And we also assume that t is a one-to-one transformation. And we want to see how t transforms a small rectangular region S that's delta u by delta v units in the uv plane to a region, let's say R, in the xy plane. And figure 5.74 of the textbook, which you see here, is an illustration of what we're doing. So x is going to be g of uv, and y is going to be h of uv. And so that tells us the position vector of the image of some point uv in S is going to be r of uv. That's the vector valued function. R of uv is the vector whose components are g of uv and h of uv. Let's suppose now that u sub 0, v sub 0 is the coordinate of the point at the lower left corner that we see here, and assume that it's mapped to the point x sub 0, y sub 0. So in other words, x sub 0, y sub 0 is equal to the transformation applied to the point u sub 0, v sub 0. We see that the line v equals v sub 0 is going to map to the image curve whose function is the vector value r of the point u, v sub 0, and the tangent vector at x sub 0, y sub 0 to that image curve is going to be determined by taking the derivative of u, the partial derivative of r, with respect to u. And as we've learned, that's just the partial derivative of those points, and that should equal, that's the vector's components of the partial derivatives of x and y with respect to u. Similarly, if I look at the line u is equal to u sub 0, that's going to map to the image curve with the vector function, right, r of u sub 0 v, having tangent vector again at x naught, y naught. Our tangent vector this time is going to be the partial with respect to v. And so we are going to have this. And so that's going to be the partials with respect to v of x and y. All right, so far, hopefully, so good. But looking at the definition of these derivatives, we know that the partial with respect to u of our function is going to be the limit as delta u goes to 0 of our function evaluated at u sub 0 plus delta u comma v sub 0 minus r evaluated at u sub 0 v sub 0, all divided by delta u. Multiply both sides by u sub 0, and we get that r of u sub 0 plus delta u v sub 0 minus r of u sub 0 v sub 0 is going to be approximately delta u times the partial with respect to u. And similarly, right, we could do the exact same thing with our partial with respect to v, except in this case, what's going to happen? In this case, we're going to have r of u sub 0, v sub 0 plus delta v, right, minus r of u sub 0 v sub 0, and all divided by delta v. So again, we're going to do the same thing. We're going to multiply through by delta v, and if we do that, what we obtain is that this difference is approximately going to be, that's an approximately, by the way, delta v times the partial with respect to v. Okay, so we can approximate now the area delta A of our image by finding the area of the parallelogram formed by delta u r sub u and delta v r sub v. And how do we do this? Well, from the previous chapter, we know that we're going to find the cross product of these two vectors. Now you might say, wait a minute, they're not in R3. It's okay, we'll just take the third component, the kth component, to be 0. So delta A is going to be approximately this the magnitude, no, let me try that again, sorry. Delta A is going to be approximately this cross product, the magnitude of the cross product times delta U, delta V. So what we're going to have is the cross product is going to be the determinant of the matrix whose components are these guys. And if we do our determinant properly, this is what we're going to be left with, because when we take the first two components of the derivative, that's going to give us 0, and we're just left with the third component. Now we're taking the magnitude of this. And when we take the magnitude of this, right, the magnitude of the vector k is just 1. So I'm going to have that this is true. And so my delta A then is approximately just the value of this determinant. And we talked about how to evaluate these determinants, but just a quick reminder that the determinant of a 2x2 matrix, if you'll recall, if I can get things to work, if you'll recall, right, we multiply down and that gets added. So it's a positive. We multiply up and we subtract. So that gives us AD minus BC. And this is a special object called the Jacobian of our transformation. It's denoted by J of UV, and actually it also has another notation, right? Some people denote it with partial of xy divided by partial of uv, the absolute value of that, or determinant. And it's just the determinant of that matrix. It's just the one we just found. And this definition, I have no idea why I have this twice. So again, what you want to keep in mind is this is the Jacobian. And now, since delta A is approximately the absolute value of the Jacobian times delta U times delta V, we can go back to the definition of the double integral using Riemann sums, use the transformation to rewrite the integral, and that's going to give us the double integral over R of f of x, y, dA is equal to the double integral over S, f of g of uv, h of uv, absolute value of the Jacobian, times du dv. So I couldn't very well write absolute value easily. So absolute value of the Jacobian, that's it. So again, S is the region in the UV plane that maps into the region R in the XY plane. By that transformation, T of UV is the point whose components are G of UV, H of UV, right? X is G of UV, Y is H of UV, and I'm going to do the examples on the next video so that you can pause here, review what we've done, and reflect.